evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. Tonight we're going to focus on AP Precalculus Unit 3. And maybe you're thinking, hey, what happened to Units 1 and 2? We already did that. That's old news, but have no fear in case you missed it. I'm going to send a link where you can view the on-demand webinar for the first 2 units that we did some weeks ago. So again, tonight is AP Pre-Calc Unit 3. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make those tough to teach, tough to learn concepts accessible to all my students. And with us tonight is Gail Burrell and Rachel Gorsuch. Gail is currently an academic specialist in the program for math ed at Michigan State University, and she was a secondary math teacher in Milwaukee for over 28 years. She served as president of NCTM and the International Association for Statistical Education. She also has won NCSM and NCTM service awards. And currently, she is also a senior math advisor for Texas Instruments. So, Gail, it's great to have you with us.
Great to be here. Thanks, Mike.
And Rachel is a teacher at Teays Valley High School, teaching data science, geometry, and Algebra 1 this year. She is a co-author of the textbook Precalculus, Graphical, Numerical, Algebraic, AP Edition, and taught Precalculus and AP Stats in recent years. She is also a huge fan of teaching modeling and co-wrote Ohio's Mathematical Modeling and Resource course. So Rachel, it's great to have you with us as well.
I'm also excited to be here.
All right, Rachel, can you talk through the agenda for tonight, please?
Absolutely. Well, first, we want to welcome everyone. Gail and I are both really passionate about what we're going to present tonight, and we hope that you feel welcomed and part of the conversation. We're going to be pretty busy with the chat, so we hope that you stay engaged with that. We're going to be exploring trig functions today using regression and real-world phenomenon. We're also going to use models to describe characteristics such as amplitude, vertical shift, period, and phase shift. And then we get to play around a little bit with polar functions that are through some connections to sinusoidal functions in real world application. TI-Nspire. And then I can't forget about it. Mike's going to do a webinar drawing.
Thanks so much, Rachel. And Gail, can you talk through our expected outcomes for tonight?
Sure. So tonight we're actually hoping that when you're done, you have a good sense of how to model data with sinusoidal functions, describing characteristics with sinusoidal functions, and explore graphs and their connections, polar graphs and their connections to sinusoidal functions.
Thanks so much. As Rachel mentioned a minute ago, we are going to be using that chat window tonight to send general messages. If you have any specific questions for Rachel or Gail, use that Q&A window on the right side of your screen. And as a reminder, this session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. So without further ado, I think, Rachel, it is all yours to start.
Thank you, Mike. And I'll just get this shared. Okay. Gail.
Okay, so we're going to talk about Unit 3, but overarching across all of the units is the 3 mathematical practices for advanced placement pre-calculus. And these skills are also part of the calculus. And actually, if you step back, I think they're pretty good to have no matter what course you're teaching in high school. And so we care about procedural and symbolic fluency, multiple representations, and communication and reasoning. Those are pretty important components of how we make the instruction take place in our classroom.
Sorry, folks. I just realized I've got my one screen on my other screen. There we go.
So the next slide that Rachel's going to pose up here is got the units, that the components that go into Unit 3. Have you got that up, Rachel? There we go. And you would expect this to any kind of standard unit on trig. It looks pretty much the same. The big ideas are the same. And probably the new thing here is the polar functions. Next slide. And here, basically, Rachel and I kind of tried to identify a couple of things. I think that defining the period of a function using symbols to think about is the smallest value k such that f at x plus k equals f at x. I think that's a kind of a unique way. It's not the way I taught trig. In the notion of period, I kind of was more informal. But I think it's good for kids to see that symbolically what that means. Limit notation is a common new thing in the pre-calculus, but there's not a lot of it in what we're doing tonight. Thinking about the unit circle. These are all things that are slightly different, especially 3.5, the whole section on 3.5. Next slide, please. So we're going to be particularly paying attention to that way of thinking about the period, changes to the trig functions, the idea of a unit circle, and then the characteristics of the graph of a polar function. I will point out that we're not talking about identities, but the CED does not have students prove identities. They have that indicate students should be able to rewrite trigonometric expressions and using some of the fundamental identities, like the Pythagorean theorem identities, but they're not expected to actually prove identities. If anybody wants me to go on to why that's a good idea, I'll tell them, but we don't have time right now. Next slide.
So I wanted to share an activity I do with my students with you. I actually got this from an 8th grade earth science activity on TI's website. And before I share anything about the activity, because I get ahead of myself sometimes, I just want to have you look at this table. And if you have a pen and a paper somewhere nearby, if you could go ahead and jot down some ideas for what your estimates are for the illumination of the moon on different days during the lunar phases. So I'm going to give just a moment for you to write this down. And I want you to think really carefully as you're coming up with the numbers for these blanks. How are you trying to figure out what to put in those blanks? Do you have a strategy for trying to think about how you're going to move through this table? Is there a feature of what you know about phases that you're going to use to figure this out? And as you think about this, what I want you to do is I want you to type an answer into the chat, but don't hit enter. Just type your answer in. And then I want us to all kind of come together and read a lot of these responses. So, and I might need your help, Michael and Gail, reading through the chat, because since I'm sharing my screen, I'm having trouble seeing it. But
On it. Got it.
awesome. Okay, so hopefully you've had some time to think about how you're going to fill in this table. And hopefully you've had a moment to go through and write a couple ideas down. And at this moment, if you want to hit enter and share your ideas in the chat for what you're looking for to help fill in this table, and then Gail will help me read by reading these out.
So we've got day 1 equals day 28, day 2 equals day 27, and so on. So he's building it to kind of repeat. Average between the percents.
Nice. Any other ideas?
The max is 14. Oh,
Ooh.
she's a little worried about her. She typed something and wasn't sure.
So I love all these ideas, and students don't always think of that idea that when we're going through a phase like this or through a cycle, that day 1 and day 28 are going to have something in common, or the fact that as we move forward through the cycle and backwards through the cycle, they're going to share this symmetry. And I really love starting my periodic functions with students with this activity because they start to think about these things. Now, I went ahead and put this information into my TI-84, and now I just got to make sure I pull it up. I'm sorry, folks, I'm running 2 screens today, so now I just got to find where I'm at on this one. There we go. I think I'm in a better spot. So I went ahead and put it into my stat, and I hit 1 for edit, and I put in my estimates here. So I know my days of my lunar cycle, and then I just played around with this idea for my L2. I used a lot of your same ideas that I realized the beginning and the end of my cycle should kind of mirror each other. So I tried to include that in my list too. And then sometimes I just found the average between the values if I wasn't sure, because that's what my kids would have done. And I would love to see this now. So I'm going to go ahead and make sure my plot is turned on. And I did turn that on earlier. Let's just double check and make sure that that's my L1 and 2. We are good to go. And we're going to graph that. And so then I always ask my students, I'm like, how do you know how good your estimates are? And they say, well, you know, it's a good curve up and down. And some of my students who had stats with me, they also think it looks like a normal curve, which I don't know if your students ever say that, but they always say that like one piece of the sign looks like a normal curve, and we have to have a conversation about that. But I think it's kind of cool that we could actually use a regression, try to see what's going on with this. So if we go to stat and we go over to calc, then we go all the way down until we see, Gail, can you help me out? I have my closed captioning is actually right up. Oh, there we go. Just got that moved down.
Yeah.
Perfect. So C is sign regression. And I just want to make sure it says 3 iterations. I'm actually going to do just 1 iteration for this using list 1 and list 2. And I always tell I need to include the period of my function in this. I'm going to try 28 days just to see if that's going to be accurate. And then I'm going to store this in my vars as I think I have something stored already. So I'm going to do Y2 just to try to make sure I don't overwrite anything. And there is that beautiful function right there. So I'm going to tell you, I was playing around a little bit earlier with the idea of a polar function. So I need to go back to my function screen and my mode. And I'm going to go to the Y2, which is where that sine function is graphed. And I just want to see what this looks like on top of my estimations. And I wonder what you guys think. I've got my chat up now and kind of everything sorted out. What do you think? Do you think this is a pretty good line or curve of best fit? We'll call it that. Do you think it's pretty good? Or do you think that we have any points that need to be moved? So I'm looking for the chat. What are your thoughts?
Very good. Very close. They're liking it.
Oh my gosh, you guys are too nice to me. This is what I was trying to do during dinner. Oh, you guys are so, it is pretty close, right? Now, one of the things that I've noticed a lot of people talking about in the AP Facebook group is this idea of a residual. It might or might not be something new to us to do a residual. And while you might not necessarily to do regressions with sine functions for AP, I think just talking about residuals again and again and again is a good strategy so that students continue to know what they're looking for and they feel comfortable. So if we want to see the residual for this, we can go into stat. And actually, I want to go into edit because I just want to put my residuals up in one of these lists. And I'm going to put it in list 3. And I can just go into my list and go to residuals. And I'm going to hit enter. And there's my residuals there. And I really want to see a graph of the residuals, but right now I'm kind of looking for, do I have some above? Do I have some below? And that's what that positive and negative is indicating to me. But really, I think I'm going to benefit a lot from seeing this residual. So I'm going to go into my stat plot here. And I'm just going to change that first plot for just a moment to make my Y list be my residuals. I could either do that by doing L3 because I already put that in my list, or if I wanted to, my son was pointing this out, that this is how his teacher showed him. And he was like, my teacher knows better than you, Mom. And I might have politely told him that we both know the right way to do this. So we've got that curve right there. And I want to change these settings because those residuals, when we looked at that list, and this is why I do this sometimes with my students first, I go to my list and notice these are all really, really close. Students will say to me, they're like, my graph is all messed up. And I'm like, your graph is not messed up. They're like, yes, it is. I'm like, look at your residuals. They're so small. And so when we're doing this, we can think really intentionally about what we want our Y max to be. And in this case, I think we could probably maybe make that Y max a lot smaller because all of our residuals are so close. So I'm going to do a 0.2 for my Y max. And then when I look at, I've got those residuals. That's the distance away that each of my estimated values, and I'm calling them estimated values because I put them into that chart as an estimate, but a lot of times when we're doing this, it's a data point. That's how far away they are from my predicted sine curve. And folks, so, oh, I'm starting seeing the thing. Anticipated sine curve. Derek, that's another way of doing it. Sometimes I think that when we're trying to show residuals to kids, there are actually like 4 right ways to do it. And so if you have a way that you really like, I have sometimes a roundabout way of doing it just to get students to think really carefully about all the pieces of a residual. But I love that you're making that suggestion. So right now we are looking at this, and I'm wondering if you guys think that this is a residual that's indicating a good model, or that it's indicating that maybe it's not the best model. So as we look at this residual, what do you think this residual is telling you? And if you could put that in the chat, I would love to see your responses.
And while they're putting that into the chat, I just want to add that one of the things I discovered about 84 and Nspire is there's lots of ways to get to an answer. My kids used to ask me, so why didn't you tell us about this? And I was like, because I didn't know about it. There's always another way that I didn't think of.
Yeah, I love having my own children be taught by teachers. They go to a school in a different district than I teach in. And it's really great because I'm learning stuff from my kids because they have these great teachers who are sharing things. We're a little quiet on the residuals, or maybe typing right now. Susanna says it's a pretty good model.
Yeah.
Amy, I agree. The model tends to be a little bit more messy. We have some above, we have some below. We're looking for no pattern until we get to the very end, and then I must have kind of screwed that up. And Jim, you're absolutely right. My residuals kind of are a little wonky there at the end of my lunar cycle. So what I would have students do at this point, and I don't want to do it tonight just because Gail's got amazing stuff and I got to pass it over to her really soon, but I would actually have students go back in and change their estimates to try to change this residual to make it a better residual, one that doesn't have a pattern, one that has about the same number of points above that axis, which is our curve that we're making a prediction for. So I would probably have them go back in and change some of their estimates and see if they could get a better residual. It might have been Stephen. It might have been. So that's my little activity that I use to get students starting on thinking about the what trig functions look like And then I would definitely go through and do a regression with them, have them think about the residuals. Always, someone had mentioned we should have known it was a sine function because a cycle really lends itself to this periodic function. So these are all tools that we have to validate models, the context, our residual. But as we're looking at these, there's really cool things going on as well, like the points of inflection. We don't have calculus to explain points of inflection in this course, but I don't know that that necessarily is a bad thing, because if we have students come up with this difference list, and I'm just going to pull this up real fast, and then Gail, I promise I'm going to switch it over to you because I can't wait for you to talk about your data stuff. But if we go back into that list that we had, right now, L3 is our residuals. I'm actually going to change this for right now. And I'm going to, for L3, I'm actually going to make that delta list. And that's one of the list functions. So if I go into second list and go over to operations here, I can actually do a delta list. That way I can, oops, sorry about that. I got ahead of myself, just like my students do sometimes. And there's not a problem with that. So I'm going to do a delta list of L2. Oh my golly. This is where I would tell them just to slow down and take care of things. And I'm going to do the same. There we go. Second to L2, double check your work, then hit enter. There we go. And so I would be asking them, what would you be looking for in this change or this delta list? And for some students, they're so used to looking for a range with lines that they would be for either a constant difference like they do with lines, or if they were playing around with exponentials, they might be looking for a constant proportion. But here, what they're actually going to be looking for is a curve. They're trying to find where it's increasing, and then the rate at which it increases kind of slows down. And so we're actually looking kind of for like a sine curve here. And so that's what we're looking for here. And I know I have some mistakes, but we do see that it goes up to about 0.15, and then we head back down. And that's what we're looking for with this this difference. Gail, is there anything else that you want to add to this? Or
I would just throw in, for those of you that teach calculus, you might play around with whether or not the rate of change that Rachel's talking about turns out to be the cosine curve, because that's what the derivative of the sine gives you. So that's just another little thing you might use in another space, not in pre-calc. Thanks, Rachel.
And Gail, when we were doing this too, setting up for this, I thought it was really cool talking with you, because you pointed out that using the calculator, we get this graphical representation, which is what we're used to with graphing calculators, but we also get the numerical part of it, which sometimes is overlooked. It's kind of like, oh, you have a table and hurry up and get it in so you can see the data. But sometimes looking at the table is really, really helpful too. So I just want to encourage people to do that.
Great. Okay, so this you guys probably know, but just wanted to kind of level set that the sine and cosine are the big ideas. They come from unit circle and radian measure, mapping values from a number line. So we used to, in my school, we taught this in Algebra 2, and we would actually take a big measuring tape, one of those ones that are kind of clothy, and we would had a big circle that was a stable circle, and we mounted up on this cardboard backing, and we thumbtack the end of the zero of our tape, and we'd wrap it around the circle, and we thumbtack it at 3 pi over 2, and at pi, we thumbtack it at all those places, and the kids could see that the one radius was what was the same thing as one radius, one arc kind of up on our circle. So they could make that association between a radian and measuring the arc length that was associated with an angle. That was a really big deal. And I do have to point out, this also comes from calculus, that the radian measure is absolutely essential when you're working with any other kind of measurement unit. Because, for example, in calculus, we have things like sine theta over theta. And if you're not working in radians, which are linear measures, then you have mixed units, because in sine theta, sine of theta is the y, it's the vertical distance, so it's a linear measure. Over theta, if theta is not a linear measure, you have a nonsensical statement. You have a linear measure, like some kind of inches or some kind of centimeters or whatever, over a degree, and you can't do anything with it. So radians are absolutely essential as a way to navigate when you're working in real contexts that involve measurement. Next, Rachel, you have anything you want to add here?
I just wanted to say that when I talk to my students about this as well, I tell them that a radian is really the measure of the arc length around the outside of the circle. And then you can draw like those wagon wheel spokes into the center. And I feel like once I started explaining it that way as like an arc length, it made a big difference to them, because they were trying to fight me. They're like, why, if I know degrees or an angle, why would I learn radians? I was like, well, because radians actually that arc length as well. And they're like, oh, wait, it's doing two things? Well, that's kind of cool. And so I just think that taking that time to answer those questions for students and encourage them to ask those questions is worth it.
Way worth it. Great. And the next slide, please.
So when we were
The
looking
other
at,
part, go
sorry,
ahead.
when we were looking at this, I
Okay.
remember that I was making this connection between what we've got with the unit circles and these dilations of unit circles. And we love our unit circles as pre-calc teachers, but reminding students that really most of what we're doing is a dilation of a unit circle, I think is a really important point to make. Back to you, Gail.
Okay, right. And that dilation says you can go to any circle. And once you have the circle, the triangles that you can form from taking a point on the circle gets you back to the similar triangles. And so you can take that triangle right out of being anchored to the origin and put it anywhere. And it gets you the connection that you need to the kind of Pythagorean definition of opposite over hypotenuse and things like that. So these definitions all connect, even though what we do in trig is the unit circle approach. Next slide. And I'm always trying to help kids think about, and trying to give options where kids can look at things and try to reason and think. I actually am trying to get things that are not Chat GPT questions, where they are looking at this graph, and it could be anybody, and they have to tell me something about one of those conditions, one of those expressions, and how they might relate to that graph. And they can tell me one that could work or one that couldn't work. But I want them thinking about the characteristics of the sine and cosine functions and how that would show up in those graphs. Next slide. And just for your background knowledge, about a third of the exam is on Unit 3, which is no surprise. And they're pretty clear about what the exam is going to look like. And there are some great sample questions that are in the CED. And also, I think there's a sample exam online. Next one. And this is an example of a possible exam question. And notice the language about increasing at an increasing rate to increasing at a decreasing rate. That's the same kind of language that Rachel was talking about with the lunar activity. And it's the same kind of language that is occurring in the other Unit 1 and Unit 2, where you're doing polynomials and you're doing exponentials and logarithmics. So this language about increasing and decreasing and concavity, that's language that is used all the way throughout, and you will see it being repeated. Next slide. All right. So this is not news to you guys, the effects of climate change. So there's been a lot of climate change news, and some of you have probably been affected by it. Next slide, please. And the deal here is that CO2 is necessary to breathe. I bet not many of us knew that 350 to 450 particles per is acceptable, but anything less than or over 600 is going to be dangerous. When you get around to 1000, you're going to actually have observable effects on thinking. So there's a limit, and that's why people are really concerned about what's going on. So Rachel's going to go to her Nspire right now, and we are going to try to do a tag team because my computer is totally slow and there's a big lag time for whatever reason. So Rachel is going to follow my directions. So she's now looking at an Nspire file, which Mike will make available to you. And page 1.2, if Rachel goes to that, you'll see the data on monthly CO2 levels and the yearly means from 2006 to 2022. So we're going to actually go to open up a data and statistics file. So Rachel's going to open up a new file. And she is going to plot a dot plot where she's going to make the horizontal axis the month.
Got a lot of variables here, Gail. I just got to find it. There we go.
It's down there. Remember, it's in alphabetical order. Okay. And then she's going to add the Y variable, and she's going to add CO206. She's not going all the way down the line here. Way up to the top. Yep. Up to the top. There you go. And there we are. Look at that. It's a sine wave. Or it looks like a sine wave, or it looks like a cyclic thing, or whatever. Now she's going to add a variable. So she goes to the left margin and doesn't want to change the variable, pull out a little bit. You're going to add a Y. Yep, you're going to add a Y variable. And you're going to add 2008. I just went every other year here. CO 2008, CO08. There you go. And we see another kind of looping up and down. So let's add one more. So if she goes and adds another Y variable, let's do 2010. And we see this kind of pattern. If she goes to page 1.4, what do you notice and what do you wonder? These are the CO2 levels by month. 1 is January, 2 is February, 3 is March, for years 2006 through 2022. Right, type in the chat. What do you notice? What do you see?
And Gail, while they're typing, I'll tell you what, when my students learned that they could add multiple Y variables and compare multiple years on one screen, oh my gosh, it was so exciting.
All right, somebody noticed they peak in the same place. Amplitude, ooh, that's interesting. We're going to come back to that, Krista. That's pretty cool. What else do you notice? Does it anything? Same wave pattern, all highest in the spring and lowest in the fall. All right, you guys are getting it. So it looks like a wave pattern. So Rachel, let's open up a new data and stats page. And let's do month again. Sorry, it's all the way down there. Okay, and let's pick CO06. Okay, and let's check. No, we're not going to add any more variables this time. We're going to actually go to menu. So we're not going to put anybody else. We're going to go to menu and we're going to do a regression, just like Rachel did before. So number 6, regression. This time she has to go all the way down to A.
And notice on the TI-84, it made me input the period, whereas the Inspire doesn't. Depending on which calculator your students are using, make sure you run through this once beforehand, just to make sure you know what it's going to ask.
Great, good point. All right, and look at there, we've got a great cool sine wave. And let's look at the residuals, just like Rachel had us doing before. So we can go into analyze again, residuals, and we want to look at the residual plot. All right, so that one looks a little not, it looks like it has a little pattern to it. Kind of the ends are high and the middle is high and it's kind of wavy, just like that doesn't, the dots look a little bit off. We'll come back. Let's go to the next page, page 1.6. All right, so I'm gonna just have you guys stop now and look at those three graphs. The two bottom ones are 2006, 2010, and the black one is 2022. It's the CO2 levels from 2006 and 2022. What do you notice here? We can pretty much assume they're probably all sine waves, but there's something that's pretty interesting here. I think anyway. Increasing levels each year. Great, great. Okay, so Rachel, go to the next page, 1.7. Click on the page to make all that stuff go away. Just, yeah, click anywhere on the page. This is an artifact. It makes that I type the stuff in here. Okay, so in order to get both of those equations done at the same time, I actually typed one of them in and one of them is active, or maybe I typed them both in. But the thing I really want you to look at, hey, there, Sherry did it. The graph is flattening out a little. Do you see that? Look at the amplitude. The amplitude in 2006 was 2.8. The amplitude in 2022 is 2.298, just about 2.3. And that's a consistent pattern. The amplitude is shrinking as the years go on. And a really good question is what does that tell us? Is that a good thing or a bad thing? It's clearly a part of the global warming, but what is actually going on there? It's a good question for your kids. And a lot of you pointed out that it's increasing each year. That's at constant on the end. So look at the 382 in 2006 and the 418 in 2022. It's increased 36 units, parts per million. Okay, that is a big increase in just the time from 2006 to 2022. What is that, 14 years? I don't do arithmetic very well. All right, and the other thing you can look at is the period, and the numbers inside there that would help us decide the period are actually pretty similar. Now there's a question here that oh, look at there. Christine pointed out that we have vertical translations. That's really good. Because that's really what's going on here. Those constants at the end are the vertical translations. And the period, if you think about this, it's not quite going to be exactly 1 year, which is what one would think about that it would be, because it's shifting. So you might have students investigate what the period actually is. And you have the numbers in there that you could figure it out. You could also figure out whether or not it really is a sine curve, and the fact that does it divide into the peak is that exactly, or the kind of zeros out in one, and then does month 7 zero out again, or is it a little bit beforehand? So you might actually try to have students figure out how those things work to see really what's going on here. Next slide, please. And we already talked about everything on this next slide, so we're good. We can go on to the next slide. Oops, back up. Sorry.
No problem.
Okay. All right, insert a page.
Another data and
Data.
statistics.
Data and stats, yeah. And this time we're going to make those box plots that you saw. So you're going to click and add just 2022. Sorry, but you have to start at the top. So you're going to add 2022.
Oops. Do you want me to add this on the x-axis?
On the x-axis, right. We're doing on the x-axis. Okay. Then let's add another x variable. Let's add 2021. And we could add another one, but we don't have to. Let's make them into a box plot.
So we'll go to menu, up to
Menu, plot type, box plot. And you can just see there, you can see the median, you can see that the variability in 2022 was a lot less than 2021, which maybe had something to do with the leftover impact of COVID. You know, I don't know, you could think about those kind of things. But if you go to page 2 now, to 1.10, you can see if we continue to make them, that we get this kind of visual impression. Each one of those boxes represents the range and the interquartile range of the CO2 levels for that particular year. This goes all the way from 2007 all the way up to 2022. Don't ask me why I left off 2006. But you get a pretty good impression of what's actually going on. Any questions or thoughts or comments or anything?
Yeah,
So let's go.
While they're typing, I just want to, I love that they all jumped right onto this idea of here's a real life situation, a real life cycle, and it's not a Ferris wheel this time around. It can actually function and what the amplitude means in practice. And I think that it's really powerful for students just to have the real life models that they can use their knowledge about life and the weather and what they hear on the news to help make sense of the math. And so I think these things are really important.
I agree. And actually, and the kids find it really fascinating to see really what's going on. Okay, so this leaves me with this impression that the change, yes, Sherry, kind of a linear increase of box plot medians. So I don't have the medians, but I have the means. And so we're gonna have Rachel do another data. No, we're gonna do another back to 1.10. She's a really good follower. We're going to insert a data and stats. And this time we're going to go to the bottom. We're going to put year for our horizontal axis. And our vertical axis is going to be means. And there, Sherry's impression looks really good. It looks pretty linear. So let's do a regression, Rachel. So we go to menu, analyze, regression. Let's do a show linear. Whichever one you want, because they'll be the same. Oh. So here's a space where sometimes I skip over this and I really shouldn't. You should take time with your students to say, all right, what does that 366.4627 mean? What is that? What is the 2.3538? And I got to tell you, when I've done this with my students, when I remember to do it, to really make the point, because that's what they're supposed to be doing, is interpreting this stuff. If I say, what is the 2.3538? They will tell me it's the slope. And I will say, no, it's the slope. What is it? What does it mean? It's the change in the y over the change in the x. Oh, what does that mean? And it takes a long time of me trying to say, okay. Eventually somebody will say, for every 1 year, there's an increase of 2.35 parts per million in the CO2 levels. And that's what this is all about. It's not just about recording the numbers, it's about translating that. That's 2.35 an increase. Remember, we can only get to 450 or then we start being on the okay range. And 2.35 per year, that's pretty interesting. Okay. And Becky's adding some stuff in there about the y-intercept. That's great. All right, what do we do now, Rachel? Once we got the model.
Always a residual. I love a good residual. So analyze down to residuals. Do you want to show the squares or the plot, Gail?
Let's show, well, you can show the squares just so that they know, because that's what the least squares linear regression does. So we can show the squares. Where are the squares?
They're so tiny.
They're so tiny you can't see them.
Maybe we'll do the other
That's
one.
the smallest sum of squares I've ever seen.
I think so too. I didn't expect that.
I didn't either. Okay, let's do the residuals and let's show the residual plot. That's too funny. All right. And what do we think? What do you guys think? Do you like those residuals or not?
And Gail, while they're typing, I know we're hitting residuals a lot in this, but I just keep seeing it in the AP Facebook group, the AP Precalculus Facebook group. And I think that just the more we as teachers get experience with them, especially if it's something new to us, and the more we talk about it with one another, just we're going to be even better as teachers.
Great. Okay, you guys are thinking that's not too good, but I'm actually probably going to disagree with you. If there is a pattern, if there's any predictability at all in the residuals, then I don't really have the best model I can have. And here, the predictability is that from 2006 to 2010, the residuals were positive. From 2010 to 2018, they're negative. Now from 2018 to 2022, they're positive again. So I'm seeing a pattern here. And I could predict. I mean, if I were to look halfway between the year, the year 2014 June, I could tell you where that residual is going to land. That's not a good thing to happen. Your models should not have a predictability feature in the residuals if they're a good model. And so I'm like, this is not a really good model. In space of time, we could go through, do a whole bunch of other ones, but I would just want to get through this whole thing. So you could check other regressions, but we're going to skip that one right here. We're going to go to 2.2. And so one of the things that what I just didn't show us, it didn't take into account the cyclic stuff. So we're going to look at 2.2. You're going to go back to insert a data and stats page. And I have to really hurry this up so we can get this done. So you've got time to do your polar stuff. We're going to put down the bottom, we're going to put year. And then we're going to put, so we're going to add year there.
And then on a y-axis, what do you want to use?
Average PPM.
And so now that we have this beautiful scatter plot of all of these, one thing I've heard a lot of people say is, oh my gosh, I see it and it won't let me do a residual right away. Just a reminder, you have to do a regression first and then a residual.
Ah, right. Yes, because the residual depends on the regression, because the residual is the difference in the predicted. And if you haven't regressed, you have no predicted. Okay, so here's the thing that we have to account for. So actually, if you do a linear model now, analyze,
Okay.
And we kind of already know a linear model is not really good. So where is it happening? Is it happening? Okay. And then I'll look at the residuals.
Oh, sorry, I did the sum of the squares. Those are bigger squares this time, but I'm going to go ahead and show my residual plot instead.
Okay, so here you can really see the cyclic nature and why the model is predictable. So we haven't accounted for that cyclic nature. So we need to think about some way to account for that. Okay, let's go to let's go to 3.2. I'm kind of just going. And then this one, if we go to the next page, this one starts from 1959, so there's more data. And that was kind of awesome to me when I went back to the beginning of what that looked like. This is the annual increase. And I wanted to just show you this because it both has those residuals don't really have a pattern. There's not much of a pattern. So that linear model is a pretty good model. And that's the yearly increase again. And it does have the R squared. R squared is not part of the pre-calculus CED. This would tell me that 57% of the variability in the parts per million in the CO2 level is explained by knowing the year. But there's other explanations that are going on. But the next slide, please, Rachel. I'm whipping through this so we can get time to finish the other things. All right, next slide. Okay, here's the 1974 on, that's what it looks like again. But if you go to the next slide. Now let's try an exponential model. So we go to regression. And we do an exponential model. And I don't know if you can see that the residuals are still a little bit kooky. And then let's go to the next slide. And the data, you have the data, you can play with all of these things. Let's just go to, okay, you're doing all right, let's go to the next slide. All right, so here you guys is the model they used. And I think this model is pretty interesting. Notice that it's an exponential model in E. I love it when E actually gets used someplace and my kids know that it's a number that's not just the number in some strange number book, like they think it's a variable. They don't think it's a constant. But it's E to this power, and the power it started in 1958 is when they started collecting the data. So that's your initial year. And the next slide is going to show you the whole, but look here at those residuals. See, this model has both the exponential and a sine wave in it. And those residuals have no pattern. So if you go to the next slide, 4.6, I just kind of wrapped it all up here. There, see there in the middle of that page? That's the model. And the questions you now can ask students, you can give them the model, you can let them, I've had really gung-ho kids play with this and try to come up with their own model. I don't necessarily show all my classes this very complicated model, but they can actually play with what if we predicted where the 450 would be? Because remember, that's the danger level. What would we consider that's what going beyond acceptable? When will we get to 600? When will we get to 450? What different models should we be using or thinking about? So there's a lot of things that kids can do here if you really want to explore it all. And so I think we go back to the PowerPoint now. So these activities can be found on the TI site. The first half, as long as the numbers are starting from the 1990s, You can do on the 84. The data are loaded in a program that you can use. So you should be able to just go to the next slide. Oop, 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 I didn't, just click through them all.
There's a lot of
When
stuff. There we go.
Yeah, when I didn't, what the real one that we were using, actually you could go back to your PowerPoint. That's really what you want to do. There you go. And so here's where you can find the CO2 data. Not all of the data can be used on the 84. It's just too slow to handle that much data. But you can do most of the things, the basic things with the 84 as well as the inspired. Okay, over to Rachel for her quick polars. Sorry, Rachel.
That's okay. I always love hearing you talk. I'm going to pull this back up with my calculator. So huge thanks to Steve Phelps, who just makes incredible files that you can manipulate here. We've spent a lot of time talking about amplitude and period shifts. And so what I really love about this file that he created is we can see this, this one would be a cosine graph or a sine graph shifted, but a cosine graph. And as we transform that graph, we can start to see how these polar graphs are created. And what I wanted to do is just make sure that you have access. I'm going to show you a tiny URL, or Michael post these files. But one of the cool things about this is just having students play around with these beautiful periodic functions and having them see the relationship first before you just tell them how to convert everything. Let them play around with this and see that relationship between this and the polar graph. And I just wanted to showcase this pretty quickly for you. It also has some tables because, again, we believe in numeric and algebraic and graphical representation. I found that the more I played around with this as a teacher, I actually started to get a better understanding of when do we draw that part of the curve below the x-axis, above the x-axis, when we're trying to convert from an xy coordinate plane over into the polar plane. So you will have access to this. I'm actually going to bring it back to, that was the fact. I also recognize that Mike is over here and going to do a drawing, and I don't want to cheat you out of the drawing. So I'm just going to do the fastest wrap up ever. And I really do hope that you take some time to play around with some of these files that we're going to share with you. I do start this out with a map that I found at the Dayton Air Force Museum, which is what I perceive is a polar graph on top of an XY coordinate plane. And I think taking time just to have students play in both worlds at the same time is really worth it. So we wanted to make sure our wrap up. This will be in the recording as well, but we included bit.lys to take you to any of these activities that we did today. And if we flew through it really, really fast, and we included some extra files as well to make sure that you have access to these. So over to you, Mike. And Gail, thanks so much for doing this webinar with me. It was a blast.
Oh, thanks, Rachel, and thanks for driving. It was really good.
Thanks so much to both of you. As Rachel just reminded me, we do have a webinar on drawing. So we are giving away to one lucky winner a TI graphing calculator of their choice. And tonight's lucky winner is Carol Edwards. So Carol, congratulations. We'll be in touch to get some information from you, but start thinking about which TI graphing calculator you'd like to receive. To download a certificate of attendance, go ahead and click the link that I posted a minute ago in the chat window. I'm going to post it again. It contains all the links that you'd want from tonight, including that really cool file that Rachel showed us that Steve created with the polar coordinates. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. When you leave the webinar, a brief survey automatically appears in your browser. Your feedback really helps us guide future events. We are planning more AP pre-calculus webinars coming next year in 2024. And so if you have something that you saw tonight that you're like, I want to see more of this, or something you haven't even seen yet that you're just dying to see, let us know. It would really help us plan our future events. And again, a huge thanks to Gail and Rachel for everything they put together tonight. Thank you so much to both of you. And thanks so much to everyone for joining us tonight. We hope you guys have a great night.
Thanks, guys.